With all the best research projects, this topic started by chance conversations with academic colleagues. So one was held in the coffee room when I was talking to one of my colleagues who's a soil scientist and explaining to him how there were problems of disposing with iron-rich ochre from a project I was working on, which was treating mining waste in central Scotland. And he had experience with tropical soils and reminded me that in tropical areas, which are very iron, aluminium rich soils, that fertilisation of agricultural land with phosphorus is always a big issue because the iron-rich compounds in these soils capture the phosphorus that is applied in fertilisers. So we came up with an idea that we could use the iron-rich ochre materials that I was having problems disposing of in my research project to capture phosphorus from wastewater. So that was the first chance conversation. The other chance conversation was with a colleague from another university at a conference field trip. So as we were wandering around mine water treatment systems in northeast England, we were just catching up on what we were researching at the moment and found that we were looking at very similar ideas. So we decided to merge forces and developed a collaborative research bid that was funded. So with that research project and how it's developed since then, we've been focusing on using two materials which can both capture phosphorus from wastewater and also release it as a fertiliser in soils. And the two materials we've been looking at are the iron-rich ochre from mining waste that I've mentioned already, and more recently, in collaboration with the UK Biochar Research Centre, also in the School of Geosciences here in Edinburgh, we've been looking at creating biochar from sewage sludge for capturing and releasing phosphorus. So I'll just talk through now our research with these two materials that we've conducted. I introduce the materials, I'll talk about some of the key findings, and then finish up by considering future directions and opportunities for this research. So I'll start off by describing ochre. What is iron ochre and how is it formed? Now, iron ochre is comprised mainly of iron hydroxides and iron oxyhydroxides, and in this case we're looking at their precipitates in mine water treatment plants that are shown in the images on the left. So these mine water treatment plants are treating water from abandoned coal mines, which were formerly widespread in the UK. And to develop more sustainable long-term methods of treating mine waters, sort of low-tech sustainable solutions like settling ponds to capture the iron precipitates in the mine water are used. And it's estimated that about 40,000 tonnes per year of iron ochre are produced across the UK at mine water treatment sites like the one shown here close to Edinburgh. Most of this material is classified as non-hazardous, so there's the potential to use it in other ways in the environment. In order to get the ochre into a usable form, we first need to dry it out, and this starts off in the field. The image here shows what these settling ponds can look like if the water's drained from them. in that the ochre dries out to the extent that we can then scoop it up and use that in filter systems and to conduct our experiments. So the first step in our research was to demonstrate the potential of these materials for stripping phosphorus from wastewater. And we started off in the laboratory using a standard technique called batch experiments, in which you shake known amounts of material with a solution with known phosphorus concentrations and compare the phosphorus concentration at the beginning and the end of the experiment. And we use the equipment shown here, called an auto-analyzer, to determine the phosphorus concentrations in solution at the start and the beginning of the experiment. And how this equipment works, the main bit of it's shown on the lab bench in the image. It works by a process called automated colorimetry, in which the introduction of chemicals to the sample causes a change in colour, and the deeper the colour, as measured by absorbance, the higher the concentration of phosphorus in solution. The technique of batch experiments obviously isn't totally realistic of field conditions, because we're using tiny quantities of sample in ideal solutions, but it does enable us to make comparisons between different materials to evaluate their effectiveness. The results that we found are shown in the table here, and these are data for the absorption capacity in grams of phosphorus per kilogram of material. So the higher the number, the more phosphorus that the material is able to remove. And you'll see that ochre samples come up at the top of the table, in that they have much higher removal capacities for phosphorus, in some cases an order of magnitude higher than other materials that have been tested for removing phosphorus from wastewater. And the reason that ochre is so good at removing phosphorus is because the iron hydroxides and oxyhydroxides that comprise it have a very large surface area for phosphate molecules to stick to. And they also have a positive charge which attracts the negatively charged phosphate molecules. And it's been shown that initially there's very rapid adsorption of phosphate onto the surface of the material. And then over time the phosphate works its way in from the surface into the mineral lattice of the material, which gives it a continuing capacity for phosphate removal. So after demonstrating that ochre was very effective in the laboratory for removing phosphorus, we then scaled up the systems and tested out phosphorus removal at real sewage treatment plants in the Scottish Borders and North East England. And the setup at one of these sites is shown here. You can see it's in the back of a trailer, so we're not treating the whole wastewater at the treatment plant, we're just siphoning off a portion of the flow and running it through our field experimental system that is shown in the image. So the ochre in the treatment system, the image is the bright red bit in the middle, and that bright red colour is caused by its high iron content. And in order to get these filter systems to work, we needed to create pellets of the ochre. When we obtain the ochre from its drying beds in the field and dry it out, it dries out to a very fine red powder, like a red dust, that hopefully you can see here. Yeah, so you see it's very fine powder, which is a real pain to move around or do anything with. And it also has a very low infiltration rate, so it's useless for a filter system. So to create something that works in a filter, my colleagues at the University of Newcastle created pellets of the ochre, and these were created by mixing the ochre with some water, with some washing up liquid and some cement on a pan pelletizer, which slowly turns and creates pellets. So it was pellets like these that we put into the filter system, and we found that the filter system had very good phosphorus removal, over 70% to begin with. But we did find there were some issues relating to clogging of the filter over time as biofilms grew within it. And we also found that the flow rate through the system had a big influence on the phosphorus removal. So phosphorus removal was best when we had low flow rates. It wasn't so good when we had high flows through the system. So we demonstrated that at this sort of smaller field scale in sewage treatment systems, that ochre pellets had good potential for phosphorus removal. The final step of the research was to look at how can we use this phosphorus as a fertiliser once the ochre or the materials have removed all the phosphorus that they can. Other researchers have directly recovered the phosphorus from ochre by passing a high pH solution through the ochre, which strips out the phosphorus, and then they've recovered the phosphorus from this solution and turned it into fertiliser. But in our research, we've been focusing on applying the phosphorus-enriched material directly as a fertiliser to soil. And we've demonstrated that this works well, both in pot experiments in a greenhouse, which are shown on the image here, and we're growing barley and grass under different fertilisation regimes in the greenhouse. We're comparing the plant growth and quality when we use conventional fertiliser treatment and when we add phosphorus in the form of ochre saturated with phosphorus. We've also scaled up these experiments again to the field, and in the images shown here, again we're looking at grass systems just south of Edinburgh. You might just be able to see in the images our field plots, which are covered with sort of wire cages to stop the sheep from interfering with our field plots, so we can remove sort of influences of sheep on the grass growth. And then the other image shows a field with plots of barley, which were also grown under the different fertiliser regimes with the conventional fertiliser and the ochre phosphorus-enriched fertiliser. And our results show great promise of this technique. We found that the plant growth and the crop yield for both grass and barley were not significantly different between phosphorus added in ochre or in the conventional fertiliser treatment. And indeed, we showed that when we applied phosphorus with the ochre, that the phosphorus concentration in the soil was higher at the end of the experiment compared to the treatments with conventional fertiliser. And this can bring additional benefits to farmers, as it means that they may only need to apply fertiliser every 2 or 3 years to an agricultural field rather than every year with conventional fertiliser. The final aspect that we tested in these experiments was to check that there was no environmental contamination effects of the ochre materials that we added to these systems, because it always is a concern when you're applying materials that are regarded as wastes to agricultural systems, is whether you're causing any additional contamination. So to test for this, we analysed samples of the soils, the plants, the roots, the stems, the barley grains for heavy metals such as arsenic, cadmium and lead. And we compared the concentrations that we measured with environmental standards and found that in all our samples they didn't exceed environmental standards. So we'd shown that there wasn't any adverse impacts of our fertilisation system. So we've done a lot of work on ochre, and more recently the research has extended in collaboration with colleagues from the UK Biochar Research Centre, and we've been looking at materials based on biochars and materials that optimise both the phosphorus attraction properties such as ochre provides and also the additional benefits that biochar may provide. So biochar is defined as the solid product of the pyrolysis of organic material, and what this means is that it's created by putting an organic material. It could be anything ranging from sewage sludge to rice husks to coconut husks into a high temperature furnace and heating it in the absence of oxygen. And that process is called pyrolysis. So we end up with a solid, often carbon-rich material with quite a porous structure. And this can provide additional benefits when applied to agricultural soils through improving the soil structure and the infiltration, and also for storing carbon in soils. So what we've been doing, in particular my PhD student Jessica Shepherd, is producing novel biochars which combine both ochre and anaerobic digestate produced from sewage sludge to see if this optimises phosphorus capture from wastewater and release as a fertiliser. So on the image here, we can see Jessica in her fluorescent jacket and safety helmet collecting anaerobic digestate from one of the Edinburgh wastewater treatment plants as a feedstock for producing these biochars. And we also have an image here which shows the small-scale pyrolysis unit at the UK Biochar Research Centre at King's Buildings, which was used to make the experimental biochars. So where we're going now in this research is in a number of directions. One of them is improving our small-scale process understanding at how soil characteristics affect the availability of phosphorus to plants in agricultural systems. And for this work, we'll be using techniques such as electron microscopy to identify what the form of phosphorus is on soil particles. So here we have a scanning electron microscope image of a soil particle, and we can see phosphorus particulates, precipitates on the surface of it. And this image is on a micrometer scale, and using a technique called scanning electron microscopy, electron dispersive microscopy, a bit of a mouthful, we can identify the composition of precise points on the surface of the soil particle. So we view the SEM image that we see here, and we can identify points of interest and touch them with a probe, which will analyse the composition of that point and produce a spectrum like the image shown here. And the peaks on the spectrum correspond to different chemical elements. And the main peaks on the spectrum we can see here are iron, oxygen and phosphorus. So using spectra like this, we can work out what the composition is of phosphorus on the soil particle surface, and this helps us understand how the phosphorus is being transformed within the system, and therefore how available it is to plants. At a larger scale, we're refining the development of materials. So in research starting soon, we intend to investigate different biochars. And we also need to consider what materials properties are important for farmers. So farmers are interested in fertiliser products which are easy to spread with their existing equipment. So we need to make sure that the material we produce is compatible with existing equipment, as farmers won't want to go and spend a lot of money purchasing new spreaders just because we come along with our fancy fertiliser. So it's always really important in projects like these to talk to farmers and find out what they're looking for in fertilisers as well. Another strand of ongoing work are further field scale demonstrations of the ability of ochre pellets to remove phosphorus from wastewater, and there are trials ongoing with a local small company near Edinburgh and Scottish Water in using ochre pellets in Scottish Water treatment plants. With all this work, we need to think about the regulatory framework as well. And at the moment, regulations in the UK and the EU are not very clear about the application of ochres and biochars to agricultural soils. However, the fertiliser regulations in the EU are currently under review, and there are inputs from the waste management community and researchers working with Biochar to see how the use of these materials can be incorporated into future management of agricultural land. So there are many different directions the research is going in, and we hope that one day we will help close the phosphorus loop and end the phosphorus paradox, in which we flush lots of phosphorus down the drain instead of capturing it and using it to promote food security.